I would like to do another demonstration of eddy currents and the resulting magnetic braking that will occur on a pendulum. So what I have here are two magnets. Okay, so this is like the north pole here of this magnet and the south pole here of this magnet. So there's a fairly uniform field in between here, and these are actually fairly strong magnets. So if I actually put a piece of steel in here, if this were a piece of steel, it would stick and I probably wouldn't be strong enough to pull it apart. But what I have here is a piece of aluminum. Okay, so aluminum is paramagnetic, so it is only weakly magnetized, so it's not really attracted to the magnets. Okay, so I also have two other pendulums. Okay, this one has slots in it, and this one, the slots go all the way to the bottom, so there's no connection along the bottom. Okay, and any of these I put in here will freely swing. Okay, so now let's see what happens when I try to swing this one through the magnetic field. Okay, notice how it breaks and stops. Now if I did the one with the slots, we see it also breaks and stops, not quite as quickly. And finally, the ones with the grooves so that there's no connection on the bottom swings freely. Okay, what is happening is that as this one is swinging into the field, you have a changing magnetic field in this region. So that sets up a resulting current such that the magnetic field generated by the current opposes the increase in magnetic field. So that will be a field in the opposite direction, and that is what's causing the braking. Whereas in this one, where we have these grooves, you can't get the circulating eddy currents because of the disconnection between these regions of the metal, and that's why you don't set up those strong induced magnetic field currents and resulting magnetic fields. Let's see if I can further clarify the eddy currents that will start to occur and the resulting magnetic field due to those eddy currents. So let's say we're sitting in that gap between those two magnetic poles, and we're looking, say, from the north to the south pole. So this circle signifies the area of one of the poles, and these X's signify that the magnetic flux density is into the page. Okay, so the aluminum pendulum now is trying to slide in like this. Okay, so as the aluminum pendulum is going in, what we see is that in this area we have an increasing magnetic field inside the aluminum into the page. So that we know is going to induce a current, so that that induced current generates a magnetic field that opposes the increasing field into our aluminum here. So that will be a counterclockwise circulating currents are going to start to set up here. So that's going to generate a magnetic field that's coming out of the page and opposing the increasing field into the page due to the aluminum sliding into the field. Now when the pendulum with the slots slides into the magnetic field area, these eddy currents cannot flow because now you have discontinuities, you have the high resistance air gaps, so you're not going to get those eddy currents and the resulting same large opposing magnetic field. So the kinetic energy of this pendulum as it's sliding in is converted to heat in the aluminum due to the eddy currents.